Look up at the night sky for just a moment, and what do you see? A scattering of stars, maybe a planet or two, but behind that seemingly quiet canvas lies a reality so strange, so overwhelming, it defies everything we think we know. Our universe isn't just vast, it's alive with mysteries that challenge the very limits of human understanding. Dark energy accelerating its expansion, galaxies vanishing into voids we can't explain, whispers of parallel dimensions brushing against our own, each one a cosmic riddle begging to be solved. Think of it like a puzzle, but one where half the pieces are missing, and the ones we have keep changing shape. What if I told you the universe is hiding 25 of its most astonishing secrets in plain sight? Secrets that could rewrite physics, reshape our place in the cosmos, and maybe even answer the oldest question of all: are we truly alone? From the ghostly pull of invisible matter to the eerie hum of background radiation left over from the Big Bang, these aren't just abstract ideas, they're clues scattered across time and space, waiting for us to connect the dots. And that's exactly what we're about to do together. This isn't just a tour of cosmic curiosities, it's a journey to the edges of knowledge itself. Every mystery we uncover pulls back another layer of the universe's grand design, revealing how much we've yet to learn. Some will unsettle you, others might make you question reality, but one thing's certain: by the end, you'll never look at the night sky the same way again. So let's begin where all great stories do, with the unknown and the irresistible urge to explore it. One of the most baffling puzzles in modern cosmology doesn't come from the edges of the universe, it's hiding in plain sight, buried in the numbers scientists use to measure how fast everything is flying apart. We call it the Hubble Tension, and it's not just a minor disagreement, it's a full-blown crisis in our understanding of cosmic expansion. Here's the problem: when we measure the universe's growth rate using nearby galaxies and supernova tools tied to Hubble's original methods, we get one number. But when we calculate it using the afterglow of the Big Bang, the cosmic microwave background, we get a distinctly different answer. These results should match, but they stubbornly refuse to, leaving astrophysicists scratching their heads. Think of it like checking your car's speedometer against the roadside radar signs, only to find one says you're doing 60, while the other insists you're barely hitting 50. That discrepancy points to something deeper, something fundamental we might be missing. The implications are huge. If both measurements are correct, our current models of dark energy, the mysterious force accelerating the universe's expansion, could be incomplete or worse, utterly wrong. Maybe dark energy isn't constant but evolves over time. Perhaps there's an unseen particle influencing gravity in ways we haven't accounted for. Or could there be an entirely new layer of physics lurking just beyond our equations? This isn't just academic debate, it's a crack in the foundation of cosmology. The Hubble tension forces us to confront uncomfortable truths. Either we've made subtle errors in our observations, or the universe is playing by rules we haven't discovered yet. Every proposed solution opens wild possibilities, from exotic forms of matter to wrinkles in spacetime itself. And until we solve it, this cosmic speed mismatch remains one of the most tantalizing clues that our map of reality might need redrawing. If the Hubble tension makes us question how the universe expands, dark matter forces us to confront what we can't even see. Picture this: galaxies spinning so fast that their outer stars should fling into the void, except they don't. The math says there's nowhere near enough visible matter to hold them together, yet something invisible exerts an undeniable gravitational grip. That's dark matter in action, a cosmic ghost holding the universe together while refusing to reveal itself. The evidence isn't subtle. Take galaxy rotation curves plots of how fast stars orbit a galaxy's center. Newton's laws predict speed should drop farther out, like planets slowing as they distance from the sun. Instead, stars at a galaxy's edge whip around just as fast as those near the core. This defiance of gravity's rules suggests an invisible halo of matter envelops every galaxy, its pull keeping stars from escaping. Then there's gravitational lensing, where light bends around massive objects. Some galaxy clusters warp space-time so dramatically they magnify distant galaxies behind them. But when scientists tally the visible mass, it's only a fraction of what's needed to create such distortion. Again, dark matter fills the gap. So what is this elusive substance? Leading candidates range from weakly interacting massive particles, WIMP, hypothetical heavy particles that barely touch ordinary matter, to actions, ultra-lightweight particles that could permeate space like a cosmic mist. There's just one problem. After decades of hunting, detectors buried deep underground in Antarctic ice, and even aboard the International Space Station, have come up empty. Every null result deepens the mystery. Could dark matter interact in ways we haven't imagined? Might gravity itself behave differently at cosmic scales? The frustration is palpable. We see dark matter's fingerprints everywhere in the clumping of galaxies, the afterglow of the Big Bang, even the universe's large-scale structure, yet it slips through our experiments like smoke. Some theorists now dare to ask, what if we're chasing a mirage? Alternative theories, like modified Newtonian dynamics, suggest gravity might strengthen where it's feeble, eliminating the need for dark matter altogether. But these ideas struggle to explain all the observations, leaving most scientists convinced something invisible is out there. Here's the twist: dark matter's elusiveness might be the ultimate clue. Its refusal to conform hints at physics beyond the standard model, hiding in the shadows of our equations. Until we crack this puzzle, galaxies will keep spinning too fast, light will bend without a source, and the universe will hold its greatest secret just beyond our reach. While dark matter tugs the universe together with its invisible gravity, dark energy does the opposite, pushing everything apart at an ever-increasing speed. This isn't just expansion, it's acceleration, as if some unseen hand is pressing harder on the cosmic gas pedal with each passing moment. The discovery of this phenomenon in the late 1990s shocked scientists, overturning decades of assumption that gravity would eventually slow the universe's growth. Instead, distant supernova revealed space stretching faster than predicted, as though the fabric of reality itself were being stretched thin by an unstoppable force. What makes dark energy so unsettling is how little we understand it. The leading theory frames it as a property of space, a cosmological constant, as Einstein once proposed. Empty space, in this view, isn't truly empty but seething with latent energy that drives galaxies apart. Yet this explanation raises thorny questions. If dark energy's strength remains constant, why does its repulsive effect seem to overpower gravity only now? Billions of years ago, matter's gravitational pull dominated, but as the universe expanded and matter thinned out, dark energy's push grew stronger. Some theorists argue this timing isn't a coincidence but a clue. Perhaps dark energy isn't constant at all, but evolving in ways we can't yet measure. This debate leads to one of cosmology's most dramatic scenarios, the Big Rip. If dark energy's push grows stronger over time, it could eventually overcome not just the space between galaxies but the bonds holding stars, planets, and even atoms together. Picture a universe where, billions of years from now, galaxies first vanish over the horizon of visibility. Then, star systems are torn apart. Finally, in a fleeting instant, molecules, nuclei, and even the fabric of spacetime itself are shredded. It's a haunting vision, but not all researchers buy it. Alternative models suggest dark energy might plateau or even weaken, sparing the universe from such a violent end. The stakes couldn't be higher. Dark energy isn't just some abstract curiosity, it's deciding the ultimate fate of everything. Current telescopes and upcoming missions like the European Space Agency's Euclid satellite are hunting for subtle shifts in how dark energy behaves across cosmic time. Each new observation could tip the scales toward one scenario or another, revealing whether we're destined for a cold, lonely expansion or a catastrophic finale. The irony is profound. The force shaping the universe's destiny remains almost entirely hidden from us, its secrets locked in the vast emptiness between galaxies. Until we crack this enigma, the cosmos will keep expanding faster, carrying its greatest mysteries farther out of reach. Even in a universe expanding at breakneck speed, some forces refuse to let go. Hundreds of millions of light-years away, something colossal is pulling entire galaxies, including our own Milky Way, toward it with irresistible force. Astronomers call it the Great Attractor, a gravitational behemoth so hidden behind thick veils of interstellar dust that we've only glimpsed fragments of its true nature. Imagine trying to spy a distant city through a sandstorm, catching only fleeting shapes through the swirling chaos. That's the challenge scientists face when mapping this cosmic enigma. At first, the Great Attractor appeared to be a massive cluster of galaxies, its gravity warping the motion of everything around it. But as observations improved, a stranger truth emerged. This isn't just one dense knot of matter. It's part of something far grander, the Laniakea supercluster, an unfathomably vast web of galaxies spanning 500 million light-years, with the Great Attractor acting as its gravitational heart. Yet even that explanation feels incomplete. The sheer scale of the pull suggests there might be even more lurking in the shadows, an unseen structure adding to the tug. The mystery deepens when we consider our own galaxy's path. The Milky Way, along with our neighboring Andromeda galaxy and dozens of smaller galaxies, is racing toward this invisible heavyweight at over 2 million kilometers per hour. But here's the twist: we're not just falling toward the Great Attractor, we're destined to sail right past it. The real pull may come from something beyond it, something even more massive and distant, like the Shapley supercluster, a sprawling metropolis of galaxies another 600 million light-years away. What makes this cosmic tug-of-war so puzzling isn't just the scale, it's the implications. If gravity alone explains this motion, why does the visible mass fall so short of accounting for the force? Some propose rivers of dark matter flowing between superclusters, amplifying the pull in ways we can't yet detect. Others wonder if exotic physics like quirks in the way gravity operates across vast distances might be at play. The Great Attractor isn't just a destination, it's a signpost pointing to deeper layers of the universe's hidden architecture, reminding us that even as galaxies rush apart, the cosmos is still tightly bound by forces we're only beginning to map. Every new telescope peering through the Milky Way's dusty veil brings us closer to understanding this colossal mystery. But for now, the Great Attractor remains a cosmic siren, its song pulling us toward answers that lie just beyond our line of sight. Some patterns in the cosmos feel too eerie to dismiss as mere chance. Take the so-called axis of evil, a spine-chilling alignment in the oldest light we can observe, the cosmic microwave background. This relic radiation from the infancy of the universe should be random, a speckled portrait of tiny temperature variations frozen in time. But when scientists mapped it, they found something unsettling. Those fluctuations aren't entirely chaotic. They appear weakly aligned with the plane of our solar system, as if the universe left a fingerprint pointing directly at us. This isn't just a statistical blip. The alignment defies a core principle of cosmology, that the universe should look roughly the same in all directions, with no privileged vantage point. Dubbed the axis of evil by skeptics who compare it to a cosmic conspiracy theory, the pattern has two possible explanations, and both are mind-bending. Either our solar system somehow casts an unexpected shadow on the universe's deepest history, or we're glimpsing something far stranger, relics of a reality that existed before the Big Bang. The first camp argues it's an illusion, a trick of incomplete data or hidden biases in how we process observations. After all, we're embedded in the solar system, and subtracting its influence from measurements is notoriously messy. Dust in our galaxy, the motion of Earth itself, even the way telescopes scan the sky could subtly imprint patterns that aren't truly cosmic. But here's the catch. As experiments like the Planck satellite refined their measurements, the anomaly stubbornly persisted, like a whisper that grows louder the more you try to ignore it. Then there's the radical alternative. Some theorists suggest this axis could be a cosmic bruise, evidence of a collision between our universe and another in a vast multiverse. Others propose it's a fossil from a previous cycle of existence, a time before time when the rules of physics were different. Imagine finding a compass in your backyard that consistently points not north, but to some forgotten city buried beneath your feet. That's the level of disorientation the axis of evil introduces. What makes it so provocative isn't just the alignment itself, but what it implies about our place in the cosmos. If real, it hints that we might occupy a special location in the universe, a throwback to pre-Copernican ideas that Earth was the center of creation. Most scientists recoil at such notions, preferring to hunt for mundane explanations. Yet the anomaly lingers, a riddle written in the universe's first light, daring us to question whether we've misread the opening chapters of cosmic history. Until we crack it, the axis of evil remains either a cautionary tale about human bias or a signpost to physics we've yet to dream of. We know the universe is filled with invisible dark matter and dark energy, but here's a twist: there's ordinary matter that's gone missing too. Not exotic particles, not mysterious forces, just the same stuff that makes up stars, planets, and even our own bodies. Scientists call this the Missing Baryon problem, and it's one of cosmology's most embarrassing oversights. You'd think tracking down atoms would be easier than hunting shadows, but the universe has a way of hiding its treasures in plain sight. The math is straightforward. By tallying up all the protons and neutrons, the baryons from the early universe's afterglow, we can estimate how much normal matter should exist today. But when we count everything visible, stars, galaxies, gas clouds, we come up short by nearly half. That's an astonishing amount of material simply unaccounted for, like balancing your checkbook only to discover half your savings have vanished without a trace. Where could it all be hiding? Enter the warm, hot intergalactic medium, or WIM. Picture this: vast, thread-like webs of superheated gas stretching between galaxies, so diffuse they're nearly invisible. These filaments, theorized for decades, are the universe's hidden scaffolding where missing baryons likely reside. The gas here isn't cold enough to glow like a star or dense enough to block light like a dust cloud. It's a ghostly haze, just a few atoms per cubic meter, but stretched across cosmic distances, it adds up. Spotting it requires more than just telescopes, it demands ingenuity. One breakthrough came from studying distant quasars, the brilliant beacons powered by black holes. As their light journeys across the universe, it passes through these filaments, leaving faint absorption lines in their spectra like cosmic fingerprints. Another method involves detecting the WIM faint X-ray glow, a whisper of heat left over from when the universe was young and turbulent. The most tantalizing clues, though, come from the Sunyaev-Zeldovich effect, where the cosmic microwave background interacts with these hot gas strands, leaving subtle distortions in the oldest light we can see. But even with these tools, the hunt is far from over. The WIM signals are maddeningly faint, buried under noise from brighter sources. Some simulations suggest this missing matter might lurk in even stranger forms, perhaps as rogue planets drifting between stars or as ultra-diffuse clouds too faint to spot. Others speculate a fraction could be tied up in the faint halos around galaxies, places our telescopes haven't yet probed deeply enough. Every time we think we've cornered the missing baryons, they slip away again, reminding us how much of the universe's ordinary stuff remains just out of reach. What makes this mystery so compelling isn't just the missing atoms, it's the humility it forces upon us. If we can't even account for the familiar matter that makes up everything we see, how confidently can we claim to understand the cosmos? Solving the baryon problem isn't just about balancing a ledger, It's about mapping the hidden highways where matter flows, connecting galaxies in a web far richer than we ever imagined. Until we do, the universe keeps a secret stash of its most basic building blocks, waiting for us to piece together where they've been all along. Black holes were supposed to be the universe's ultimate vaults, cosmic traps where anything that crossed their event horizons vanished forever, taking its secrets into oblivion. But in the 1970s, Stephen Hawking dropped a bombshell. Black holes aren't permanent. They slowly leak energy, evaporating over unimaginable timescales through a process we now call Hawking radiation. This revelation should have been a triumph, solving one of physics' great puzzles. Instead, it tore open a paradox so deep it threatens the foundations of reality itself. Here's how Hawking radiation works. Empty space isn't truly empty, it's a seething quantum soup where particles and antiparticles constantly flicker in and out of existence. At a black hole's edge, these fleeting pairs can get separated, with one particle falling in while the other escapes. The escaping particle carries away energy, meaning the black hole loses mass over time. But here's the catch: the radiation is random, carrying no information about what fell into the black hole. When the black hole finally evaporates, all traces of the stars, planets, or spaceships it consumed vanish without a fingerprint. That's where the trouble starts. Quantum mechanics insists information can never be truly destroyed. Every particle, every collision, every event leaves some imprint on the universe's fabric, like a cosmic ledger that must always balance. If black holes erase information, that ledger is violated, and physics as we know it falls apart. General relativity, on the other hand, says black holes are simply defined only by mass, charge, and spin. No hair, no details, no records of their meals. Put these two theories together and they clash violently. Either quantum mechanics is wrong or black holes aren't what we thought. The stakes couldn't be higher. If information is lost, predictability, the bedrock of science, crumbles. Imagine tossing a library into a fire, only for the flames to leave behind not even ash but empty air. That's the nightmare physicists face. Some theorists, like Leonard Susskind, argue information isn't lost but encoded in Hawking radiation in ways we can't yet decipher. Others propose black holes leave behind remnants, tiny, information-packed relics too small to detect. Then there's the holographic principle, suggesting everything inside a black hole is somehow projected onto its surface like a cosmic mirage, preserving data in a hidden dimension. Recently, a breakthrough called the island rule has offered a potential solution. It suggests information escapes not just through radiation but via quantum connections stretching across space-time, like threads linking the black hole's interior to the distant universe. Picture trying to burn a book only for its words to reappear as invisible ink on the walls of your house. Bizarre as it sounds, calculations now hint this might resolve the paradox, but the math is so complex even experts struggle to interpret it. The battle isn't just academic. Solving this paradox could reveal how gravity and quantum mechanics unite, birthing a theory of everything. Until then, black holes remain cosmic conundrums, whispering that our understanding of reality might be missing something profound. They're not just celestial oddities, they're mirrors, reflecting how much we have yet to learn about the deepest laws of existence. The universe is unimaginably vast, with hundreds of billions of galaxies, each containing countless stars and planets. Given those staggering numbers, the odds seem overwhelmingly in favor of other intelligent civilizations existing somewhere out there. And yet, when we scour the cosmos for radio signals, laser pulses, or any hint of technology, we're met with silence. This eerie absence of evidence is the Fermi paradox, a puzzle that grows more unsettling the longer we search without answers. One explanation is the zoo hypothesis, the idea that advanced civilizations might be deliberately avoiding contact, observing us like animals in a galactic nature preserve. Think of it like stumbling through a dense jungle, unaware that researchers in hidden blinds watch your every move. proponents argue that interference with a developing species could be ethically questionable, or that Earth sits in some sort of interstellar quiet zone where others agree not to broadcast. But critics counter with a simple question: would every single civilization across billions of years abide by the same rule? Then there's the rare Earth theory, which suggests that while microbial life might be common, the conditions needed for complex technological civilizations are exceptionally fragile. A planet needs more than just liquid water. It requires a stable orbit, a protective magnetic field, plate tectonics to recycle nutrients, a massive moon to stabilize its tilt, and countless other finely tuned factors. Earth might not just be lucky, it could be a cosmic lottery winner in a universe where intelligence is vanishingly rare. Others point to the Great Filter, a hypothetical bottleneck that prevents life from advancing beyond a certain stage. Maybe the leap from single-celled organisms to multicellular life is astronomically improbable. Or perhaps every advanced civilization eventually destroys itself through war, environmental collapse, or uncontrolled artificial intelligence. The terrifying implication: if the filter lies ahead of us rather than behind, humanity's greatest challenges might still await. Meanwhile, the search for technosignatures, evidence of alien technology, has evolved far beyond radio telescopes. Scientists now hunt for Dyson spheres, hypothetical megastructures built around stars to harvest energy, atmospheric pollution on distant worlds, or even flashes of light from interstellar propulsion systems. But so far, nothing conclusive has emerged. The silence could mean we're alone, that we're early arrivals in a young universe, or that we're simply looking for the wrong signs. Perhaps the most haunting possibility is that civilizations inevitably reach a point where they transcend physical forms, uploading consciousness into digital realms or disappearing into black hole computations, realities we can't yet perceive. The universe might be teeming with intelligence, just not in ways we recognize. Until we uncover more clues, the Fermi paradox remains a humbling reminder that for all our curiosity, the cosmos guards its secrets tightly. The silence isn't just absence, it's a mirror, reflecting how little we truly understand about life's place in the grand scheme. Out of the silent cosmos comes one of the most explosive mysteries in modern astronomy: fast radio bursts. These fleeting cosmic flashes pack more energy than our sun emits in weeks into mere milliseconds, vanishing before we can even blink. First discovered in 2007, these bursts arrive without warning, lighting up radio telescopes with signals so intense they've been detected billions of light years away. Yet what generates such staggering power remains an open question, turning these bursts into cosmic fingerprints, each one a tantalizing clue pointing to origins we're only beginning to unravel. Start with the leading suspect, magnetars. Imagine a neutron star, the collapsed core of a dead star, spun up to unimaginable speeds and wrapped in a magnetic field 1 trillion times stronger than Earth. These cosmic powerhouses, known as magnetars, occasionally snap under their own tension, releasing starquakes that ripple through space-time and unleash torrents of energy. In 2020, astronomers got their smoking gun when a magnetar in our own galaxy fired off a burst eerily similar to those coming from deep space. The pieces seemed to fit until researchers noticed a problem. While magnetars can explain some bursts, others appear far too energetic or repeat too frequently to match. There's also the puzzle of dispersion. As these radio waves travel through intergalactic plasma, they slow down in telltale ways that suggest journeys across billions of light years. Yet some bursts show dispersion patterns that don't neatly align with known cosmic structures, hinting at environments we've never observed. This inconsistency has opened the door to wilder possibilities. Could some bursts come from colliding neutron stars, their unimaginably dense cores releasing energy in catastrophic mergers? Or perhaps from evaporating primordial black holes, tiny relics of the Big Bang popping like cosmic fireworks? Then there's the most provocative theory, technosignatures. In 2017, Harvard scientists raised eyebrows by suggesting that certain repeating bursts might align with the beam patterns of alien light sails, massive, photon-powered spacecraft needing a focused radio beam to propel them. The idea isn't entirely far-fetched. Humanity's own proposed breakthrough Starshot project imagines using lasers to push tiny probes to relativistic speeds. Scale that up, and you might get a radio signature eerily like a fast radio burst. Of course, extraordinary claims require extraordinary evidence, and most astronomers caution against jumping to extraterrestrial conclusions. But the debate itself reveals something profound. Fast radio bursts aren't just cosmic oddities, they're forcing us to rethink the boundaries of known physics. Their sheer power challenges our models of stellar behavior, while their unpredictable timing makes them maddeningly hard to study. New telescopes like Canada's CHIME array are now catching dozens of bursts each month, mapping their origins to distant galaxies with blistering precision. Each detection peels back another layer of the mystery, whether it's a repeating burst with a strange cadence or a one-off explosion from a previously quiet patch of sky. What makes these bursts so thrilling isn't just their mystery, it's their potential as cosmic tools. Their dispersion lets astronomers measure the universe's hidden matter, like using a flashlight to reveal dust in a dark room. Some researchers even propose they could help solve the missing baryon problem, acting as tracers for the universe's elusive webs of gas. Whether natural or artificial, these bursts remind us how much of the universe's drama plays out in wavelengths invisible to our eyes. They're cosmic telegrams carrying encrypted stories of events we're only beginning to imagine. Each millisecond pulse a challenge to decode and a reminder of how much we have yet to discover. It was just 72 seconds less than the time it takes to brush your teeth, but the signal that blared into Ohio's Big Ear radio telescope on August 15, 1977, still haunts astronomers decades later. Dubbed the "wow signal" after the scribbled exclamation on the day to printout by researcher Jerry Amon, this narrowband radio burst matched exactly what scientists predicted an alien transmission might look like. Coming from the direction of the constellation Sagittarius, it pulsed at 1420 MHz, a frequency silent under cosmic noise, where hydrogen absorbs background radiation. In other words, the perfect channel for a civilization to shout, "We're here." What made the signal so electrifying wasn't just its strength, 30 times louder than the ambient noise, but its structure. Unlike natural cosmic static, it was a clean, focused tone, unmodulated and unchanging, as if someone had pressed a cosmic key and held it down. Even more intriguing, it followed the telescope's motion perfectly as Earth rotated, fading in and out over exactly 72 seconds, the maximum time Big Ear could observe any single point in the sky. That precision ruled out terrestrial interference like aircraft or satellites. It had to originate beyond our planet, possibly far beyond. Yet despite 40 years of follow-up searches, including powerful modern arrays like the Allen Telescope Array, the signal never repeated. Not once. This silence fuels endless debate. Was it a one-time event, a catastrophic explosion or collision in deep space? A fleeting burst from a rotating neutron star we've yet to rediscover? Or, as some still hope, a deliberate transmission, perhaps from an alien beacon sweeping across the galaxy like a lighthouse beam, briefly illuminating Earth before moving on? Skeptics point to less exotic explanations. Hydrogen clouds or comets passing through the telescope's field could theoretically mimic the signal's profile, though none match the precise timing or location. Others suggest reflections of human transmissions bouncing off space debris, though no known satellite or probe aligns with the event. Meanwhile, researchers like Antonio Paris spent years scanning the same patch of sky, even tracking a pair of comets that passed through the area decades later, but found nothing resembling the original signal. The WOW signal's legacy lies in its tantalizing ambiguity. It's the ultimate cosmic teaser, proof that the universe can still surprise us with phenomena defying easy classification. Projects like Breakthrough Listen now scour millions of radio channels simultaneously, armed with machine learning to flag anomalies in real time. Yet the original signal remains a Rosetta Stone without a translation, a single page torn from a conversation we may never finish. Whether it was a shout across the stars or a celestial mirage, it taught us one indelible lesson. Sometimes the most profound mysteries aren't in the answers, but in the questions that keep us listening. Just beyond Pluto, where the solar system's icy debris slowly fades into darkness, something strange cuts the party short. Astronomers call it the Kuiper Cliff, a place where the number of frozen objects plummets so abruptly it's like stepping off a cosmic ledge. Out here, billions of miles from the Sun, the Kuiper belt should be teeming with dwarf planets, comets, and primordial rubble left over from the solar system's birth. And yet, past a certain point, the belt's population crashes like a graph hitting a brick wall. The math says there's no reason for this sudden emptiness unless something unseen is lurking in the dark, clearing the neighborhood with its gravitational pull. This anomaly has fueled one of the most tantalizing hunts in modern astronomy, the search for Planet 9. Not the demoted Pluto, but a hypothetical giant up to 10 times Earth's mass, orbiting so far out it takes 20,000 years to complete a single lap around the Sun. The clues are written in the orbits of distant Kuiper belt objects, bodies like Sedna and 2495-41, whose elongated paths tilt at bizarre angles. These orbits shouldn't exist in a placid solar system. They look like they've been yanked by something massive, and when researchers ran simulations introducing a hidden planet, the chaotic paths snapped into place like magnets finding their poles. But not everyone's convinced. Skeptics argue the orbital oddities could stem from the collective tug of smaller objects we haven't catalogued yet, or even echoes of a long-ago stellar flyby that rattled the outer solar system like a pebble in a tin can. Others propose more radical fixes like modified gravity or primordial black holes left over from the Big Bang. The challenge is simple yet maddening. How do you find something that reflects almost no sunlight in a region so vast it makes the inner solar system look like a postage stamp? That hasn't stopped the search. Telescopes like Subaru on Mauna Kea scan slivers of sky where Planet 9 might hide, while astronomers sift through old survey data for faint moving dots. The Vera C. Rubin Observatory, set to come online soon, could finally settle the debate with its unprecedented wide-field gaze. Until then, the Kuiper Cliff remains either a signpost to a new world or a cosmic illusion, a reminder that even in our own celestial backyard, the most profound mysteries are often the ones we can't yet see. For decades, the Pioneer spacecraft carried a secret one so subtle it nearly slipped past scientists entirely. Launched in the 1970s to explore the outer solar system, these robotic trailblazers should have coasted smoothly through the void, their trajectories predictable down to the millimeter. Yet as they ventured beyond Saturn, something peculiar emerged, an unexplained deceleration, as if an invisible hand were gently tugging them back toward the Sun. The effect was tiny, just a fraction of a nanometer per second squared, but over billions of miles, those fractions added up, nudging the probes off course by hundreds of thousands of kilometers. At first, the anomaly seemed to defy physics. Was some unknown force acting on the probes? Could it be a flaw in Einstein's theory of gravity, manifesting only in the deep cold of interstellar space? Theorists proposed wild possibilities, from the gravitational pull of unseen dark matter to exotic energy fields permeating the cosmos. The puzzle lingered for years, turning the Pioneer anomaly into a textbook example of how even the smallest inconsistency can unravel our understanding of the universe. Then came the breakthrough, one born not from cosmic revelation but from painstaking engineering. The culprit wasn't some mysterious force, it was heat. The probe's radioactive power sources emitted warmth, and that warmth, bouncing unevenly off their dish-shaped antennae, created just enough recoil to mimic a subtle deceleration. It was like a car inching forward because someone inside was throwing baseballs backward, an effect so slight it took decades to spot, yet the pioneer anomaly's legacy endures. It reminds us that the universe's greatest mysteries often hide in the details, in the quiet discrepancies between expectation and observation. Even solved puzzles leave behind valuable lessons about humility, about the importance of questioning assumptions, and about the relentless patience required to decode the cosmos. Most of all, they prove that sometimes the answers we seek aren't written in the stars, but in the faint glow of a spacecraft's own warmth, whispering secrets we almost missed. The cosmic microwave background should be a whisper of near-perfect uniformity, a faint afterglow of the Big Bang painting the sky in subtle temperature variations no more dramatic than a few millionths of a degree. But in the constellation Eridanus, there's a patch of sky that breaks all the rules, 700 million light-years wide and colder than its surroundings by a baffling 70 microkelvin. The CMB cold spot isn't just an anomaly, it's a cosmic ghost story, challenging everything we think we know about the universe's infancy. At first glance, the simplest explanation seems to be a supervoid, a vast, nearly empty region of space where the absence of galaxies and dark matter leaves less gravity to pull photons from the cosmic microwave background, sapping their energy and cooling the light that passes through. It's like stepping into a cosmic elevator shaft where the floor's galaxies, gas, even dark matter are missing, leaving the radiation to lose energy as it climbs out. But here's the catch. When astronomers mapped the galactic distribution in the cold spot's direction, they found emptiness, yes, but not nearly enough to account for the staggering temperature drop. The void would need to be impossibly large, far beyond anything predicted by standard models of cosmic structure. That's where things get weird. One radical theory suggests the cold spot isn't a void at all, but a bruise, evidence of a collision between our universe and another bubble universe in an endless cosmic foam. Picture two soap bubbles grazing each other in a sink. At the boundary, energy would drain away, leaving a cold imprint. If true, this could be our first glimpse of the multiverse, a shadow cast by a reality entirely alien to our own. The math is speculative but tantalizing. Certain inflationary models predict such collisions should leave ring-like patterns in the CMB, and the cold spot's edges bear an uncanny resemblance. Critics counter with less exotic but no less mind-bending possibilities. Could the cold spot be a rare statistical fluke, a one-in-a-million temperature dip in an otherwise random field? Simulations suggest even in a perfectly uniform universe, such anomalies should occasionally appear by pure chance, but the odds are slim. Some estimates put it at less than 2%. Others propose primordial gravitational waves, ripples in spacetime from the universe's first moments, might have stretched this region thin like taffy, distorting its temperature. Or perhaps an ancient cosmic texture, a defect in spacetime structure left over from the Big Bang lurks here, warping reality in ways we don't yet understand. The cold spot's true nature might remain unresolved until next-generation telescopes, like the European Space Agency's Euclid mission, map the distribution of galaxies and dark matter in unprecedented detail. Either way, this icy blank on the cosmic ledger forces us to confront just how much we still don't know about the universe's architecture. Whether it's a fingerprint from another reality or simply a cosmic card dealt from an unlikely deck, the cold spot reminds us that even the universe's oldest light still holds secrets waiting to be decoded. Think of space as a cosmic sheet of paper, except this sheet might not be flat at all. For decades, cosmologists have debated the universe's fundamental shape. Is it stretched taut like an endless plane, curled into a sphere like the surface of a balloon, or twisted into some more exotic form like a donut? The answer isn't just philosophical, it could rewrite our understanding of everything from gravity to the universe's ultimate fate. start with the simplest case, a flat universe. This is the default assumption in most textbooks, backed by precise measurements of the cosmic microwave background. If you drew two parallel lines in such a universe, they'd never meet, just like on a classroom ruler. But here's the catch: flatness doesn't necessarily mean infinite. Picture a video game where walking off the right edge teleports you to the left. Space could be finite but unbounded, a giant cosmic loop where you'd theoretically return to your starting point if you traveled far enough. Then there's the closed universe model, where space-time curves back on itself like the surface of a planet. In this scenario, parallel lines would eventually converge, and a beam of light fired straight ahead might circumnavigate the cosmos to hit you in the back. Some theories even suggest such a universe could eventually collapse under its own gravity, ending in a big crunch. But observations of accelerating expansion thanks to dark energy seem to rule this out, unless our measurements are missing something crucial. Now for the wild card, a multiply-connected universe where space is folded into mind-bending shapes like a three-dimensional donut or a kaleidoscopic hall of mirrors. Imagine shining a flashlight in such a cosmos. Light might take multiple paths to reach the same point, creating ghostly duplicate images of galaxies or even entire superclusters. Astronomers have hunted for these matched circles in the cosmic microwave background, patterns that would betray space's twisted geometry. So far, none have been found, but the search isn't over. The key to solving this riddle lies in the universe's geometry. Just as the angles of a triangle reveal whether it's drawn on paper, a globe, or a saddle, the cosmic microwave background holds subtle clues. A closed universe would amplify large-scale temperature fluctuations, while a multiply-connected one would imprint distinct patterns of repeating hotspots. Current data favors flatness, but the margin of error leaves room for surprises. Future telescopes like NASA and Nancy Grace Roman Space Telescope or the European Space Agency's Euclid mission could tighten these measurements, probing the universe's curvature with unprecedented precision. What makes this mystery so gripping isn't just the geometry, it's the stakes. A closed or twisted cosmos could imply finite resources, cyclical time, or even layers of reality stacked like a cosmic lasagna. Meanwhile, a perfectly flat, infinite universe might mean we're just one island in an endless sea of untouchable galaxies. The universe's shape isn't just a backdrop, it's the canvas on which all of physics is painted. Until we map it definitively, we're like ants on a Mobius strip, unaware of whether our path leads forward or back to where we began. Down at the smallest scales imaginable, far smaller than atoms, even tinier than quarks, the smooth fabric of space-time we take for granted dissolves into chaos. Picture an ocean during a storm with waves crashing in all directions, bubbles forming and bursting in an instant. Now shrink that down by a factor of a trillion, and you've got quantum foam, a seething, turbulent froth where the very notions of here and now lose all meaning. This isn't just theoretical speculation. Quantum mechanics tells us that empty space is never truly empty. It's a boiling sea of virtual particles flickering in and out of existence, borrowing energy from the universe before vanishing again. But at the Planck scale, distances so tiny they make atoms look like galaxies. This activity becomes something far stranger. Space-time itself churns, warping and twisting so violently that microscopic black holes might spontaneously form, only to evaporate moments later in a burst of Hawking radiation. It's like the universe is constantly bubbling with ephemeral cosmic fizz, each bubble a fleeting distortion of reality. What's truly mind-bending is that this foam isn't just static noise, it's dynamic, with fluctuations that could redefine causality. On this scale, before and after might not be fixed. Wormholes could thread through the foam, connecting distant points in space for mere fractions of a second before collapsing. Some theories even suggest that the foam's structure might allow for time loops where particles briefly travel backward before continuing forward again. Imagine stirring a cup of coffee and seeing Eddy's form, but instead of cream swirling, you're watching time itself twist into knots too small to measure. The catch: we can't directly observe quantum foam. Its scale is so absurdly tiny that probing it would require energies far beyond anything our particle colliders can muster. Even the Large Hadron Collider, which smashes protons together at nearly the speed of light, only grazes the surface of this subatomic storm, yet indirect clues hint at its existence. Tiny anomalies in gravitational waves or minute variations in the speed of light across the cosmos might one day betray the foam's presence, like spotting ripples from a stone thrown into a pond we can't actually see. This leads to one of the most provocative questions in physics. Could quantum foam hold the key to unifying Einstein's theory of gravity with quantum mechanics? General relativity paints spacetime as a smooth, continuous fabric, while quantum mechanics insists everything is granular at the smallest levels. The foam might be where these two frameworks collide, a realm where gravity becomes just another quirk of the quantum frenzy. If so, understanding it wouldn't just solve a century-old puzzle, it could rewrite the rules of reality itself. For now, quantum foam remains a ghost in the equations, a place where the universe's most fundamental truths might be hiding in plain sight. It's a reminder that even the vacuum of space is alive with unimaginable complexity, and that the closer we look, the stranger the cosmos becomes. Whether it's the birthplace of new physics or just another cosmic mirage, one thing's certain: the smallest scales hold some of the biggest mysteries. For decades, conspiracy theories have swirled around an object dubbed the Black Knight satellite, a supposed alien probe orbiting Earth for thousands of years, watching humanity from the shadows. The stories paint a tantalizing picture: an ancient, intelligently designed spacecraft, possibly sent by an advanced extraterrestrial civilization, silently circling our planet. But peel back the layers and the truth unravels into something far more ordinary, yet no less fascinating. The myth begins with a mix of misinterpretations, hoaxes, and genuine space oddities. In the late 1950s, newspapers reported that the U.S. Air Force had detected a mysterious dark object in polar orbit, a claim later revealed to be Cold War misinformation. Then, in the 1960s, astronaut Gordon Cooper allegedly spotted a glowing green object during his Mercury mission, sparking speculation about alien technology. But Cooper himself later clarified that his sighting was likely a faulty instrument reading combined with the stresses of spaceflight. The legend truly took off when a peculiar piece of space debris was photographed during a 1998 Space Shuttle mission. The image showed a jagged, asymmetrical object tumbling through orbit, which conspiracy theorists quickly labeled as the Black Knight. In reality, it was a thermal blanket lost during an earlier spacewalk, a mundane explanation that did little to dampen the myth's momentum. Even older elements got tangled into the story. In the 1920s, radio pioneer Nikola Tesla reported picking up strange, repetitive signals that he speculated could be extraterrestrial in origin. Though these were likely natural radio emissions from pulsars or other cosmic phenomena, they became woven into the Black Knight lore as evidence of an alien presence. So why does this myth persist? Humans are wired to seek patterns even where none exist. A floating thermal blanket becomes an alien artifact. A misheard radio transmission morphs into an interstellar message. The Black Knight isn't just a story about space, it's a reflection of our desire to believe that we're not alone, that the cosmos holds answers beyond our understanding. The irony is that while the Black Knight isn't an ancient alien probe, the real mysteries of space are just as compelling. We've found bizarre, naturally occurring objects like the interstellar visitor Oumuamua that challenge our assumptions. And with projects like SETI scanning the skies for genuine extraterrestrial signals, the truth might still be out there, just not in the form of a centuries-old satellite spinning silently above us. The Black Knight myth reminds us that sometimes the line between science fiction and reality isn't as clear as we'd like. But that's what makes exploring space so thrilling, because who knows what we'll really find next. In October 2017, astronomers spotted an object hurtling through our solar system at breakneck speed. But this was no ordinary comet or asteroid. Named Oumuamua, Hawaiian for Scout, it was our first confirmed visitor from interstellar space, and its strange behavior sparked one of the most heated debates in modern astronomy. The enigma began with its shape long and cigar-like, unlike any natural object we've seen. Then came the real shocker. As it raced away from the sun, Oumuamua accelerated unexpectedly, as if something other than gravity was nudging it forward. The simplest explanation: outgassing, the same process that makes comets sprout glowing tails as sunlight vaporizes their ices. Except Oumuamua showed no visible tail or coma, the haze of gas and dust typical of active comets. This led some researchers to propose an exotic alternative. Maybe it was a nitrogen iceberg, a shard broken off from a Pluto-like world in another star system. Nitrogen ice could theoretically vaporize subtly enough to propel the object without leaving a visible trail. Others suggested a hydrogen iceberg, though critics argued hydrogen would evaporate too quickly in interstellar space to survive the journey. Then came the bombshell hypothesis, a suggestion so provocative it split the scientific community. Harvard astrophysicist Avi Loeb posited that Oumuamua's acceleration and unusual shape might align with a light sail, a thin, reflective structure designed to catch solar radiation for propulsion. In this scenario, the object could be artificial, either a derelict piece of alien technology or even an intentional probe. The idea drew fierce backlash, with many scientists insisting extraordinary claims require extraordinary evidence. After all, nature is full of oddities we don't yet understand. Yet the debate raised a deeper question: how do we distinguish between the truly anomalous and the merely unfamiliar? Oumuamua's acceleration, while puzzling, wasn't entirely unprecedented. Some comets exhibit similar non-gravitational kicks, albeit with visible outgassing. The real challenge was its fleeting visit. We had only weeks to observe it before it vanished into the void, leaving us with fragmentary data and endless speculation. New research continues to churn. A 2021 study proposed that Oumuamua could be a fragment of a shattered super-Earth, its rocky crust stripped away by a cosmic collision, leaving behind a dense, elongated shard. Others modeled how subsurface ices might produce just enough hidden outgassing to explain the acceleration. Meanwhile, projects like the Vera C. Rubin Observatory aim to catch future interstellar visitors earlier, giving us more time to unravel their secrets. What makes Oumuamua so compelling isn't just its mystery, it's the humility it demands. For centuries, we've assumed interstellar objects would resemble those in our own solar system. Oumuamua shattered that assumption, proving the cosmos is far stranger than we imagined. Whether it's a nitrogen iceberg, a light sail, or something even more unexpected, this cosmic scout delivered a clear message. The universe is full of surprises, and we've only just begun to explore. Galaxies aren't scattered randomly across the cosmos. They cluster together in sprawling filaments, weaving a cosmic web that stretches across billions of light years. But between these threads lie immense voids, regions so empty they defy logic. Some are so vast they could swallow thousands of Milky Ways without a single star to break the monotony. These aren't just gaps, they're cosmic deserts where the rules of structure formation seem to have been tossed out the window. Take the Boötes void, for example. Spanning over 300 million light-years, this staggering emptiness contains fewer than 60 galaxies, a fraction of what standard models predict. It's as if someone took a cosmic eraser and scrubbed away nearly everything in this corner of the universe. The numbers just don't add up. According to our best simulations, matter should have clumped together more evenly during the universe's infancy, leaving no room for voids this extreme. So why does this ghostly expanse exist? One possibility is that these voids aren't entirely empty, just sparsely populated with faint, dwarf galaxies too dim for our telescopes to spot. Like fireflies in a cavernous stadium, they might be there, just invisible to our current instruments. Alternatively, dark energy could be playing tricks on us, stretching these regions faster than galaxies can form, leaving behind hollow bubbles in the cosmic foam. But the most tantalizing theory involves primordial quantum fluctuations, tiny ripples in density from the Big Bang that, over eons, grew into the structures we see today. If these fluctuations were unusually weak in certain patches, matter might never have clumped together there at all. It's like rolling dough with pockets of missing yeast, some sections just never rise. The mystery deepens when we consider how these voids influence their surroundings. Galaxies near the edges often show strange alignments, their spins mysteriously coordinated as if the void itself were twisting space-time around them. Some researchers even speculate that voids could be gateways to other universes, their emptiness a signature of an unseen cosmic connection. Until we peer deeper into these ghostly realms, their existence remains one of cosmology's great unsolved riddles. A reminder that the universe still holds vast, silent places where the rules we know might not apply. The Moon today is a quiet, airless world with no global magnetic field, but 4 billion years ago, it may have been a very different story. Apollo astronauts brought back rocks that told a startling secret. Some lunar samples bear traces of magnetization, as if the Moon once had its own magnetic shield rivaling Earth. Here's the puzzle. Magnetic fields usually require a churning molten core, a dynamo, yet the Moon is too small to have retained enough heat for such a thing. So how did it generate this ancient field, and why did it vanish? One leading theory points to a cosmic collision. Early in its history, the Moon might have orbited much closer to Earth, where tidal forces stretched and heated its interior like kneading dough. This tidal heating could have kept the core molten long enough to power a dynamo, at least temporarily. There's just one catch: models suggest this effect would have faded within a few 100 million years, yet some magnetized rocks hint the field persisted for over 1 billion. That discrepancy has sparked wilder ideas. Maybe massive asteroid impact stirred the Moon's core like a spoon in coffee, reigniting its dynamo in short bursts. Simulations show that strikes from objects hundreds of miles wide could have pumped enough energy into the interior to reboot the magnetic engine. Others propose the Moon's outer core crystallized slowly, releasing latent heat and buoyant material that kept the dynamo churning far longer than expected. Then there's the compositional twist. Lunar samples suggest the core might have been rich in sulfur, lowering its melting point and allowing fluid motions even as it cooled. Picture honey flowing when heated, then thickening as it cools, except in this case, the honey is liquid metal swirling beneath the Moon's crust, generating magnetic currents. The real smoking gun, though, lies in the rocks themselves. Certain Apollo samples contain tiny iron needles aligned like compasses, frozen in time to record the direction and strength of the ancient field. These paleomagnetic clues suggest the Moon's field peaked around 100 microteslas, half as strong as Earth's today, before dwindling to nothing. The implications stretch beyond lunar history. If small, rocky bodies like the Moon once had magnetic fields, exoplanets with similar sizes or orbits might too, raising the odds of finding habitable worlds beyond our solar system. Meanwhile, NASA's upcoming Artemis missions aim to drill deeper, hunting for rocks that capture the field's final flickers. Solving this mystery won't just rewrite the Moon's past, it could redefine how we understand planetary magnetism across the cosmos. For now, the Moon's magnetic secret remains locked in those ancient stones, a silent testament to a time when our nearest neighbor was far more than just a cold, dead rock in the sky. In the constellation Cygnus, about 1,500 light-years from Earth, a star named KSE 8462852, better known as Tabby's star, has been behaving in ways that defy every textbook explanation. Most stars flicker slightly due to planets passing in front or natural stellar activity, but Tabby's star doesn't just flicker, it plunges. Its light dims by up to 22% at irregular intervals with no clear pattern. These aren't the tidy, periodic dips caused by an orbiting planet. They're chaotic, asymmetrical, and sometimes last for days. When astronomers first spotted this anomaly in data from NASA's Kepler Space Telescope, the only reasonable reaction was utter bafflement. The hunt for answers quickly split into two camps. On one side, proponents of natural explanations pointed to dust, not the fine, uniform dust of interstellar space, but thick, clumpy clouds orbiting the star in a bizarre, uneven swarm. Imagine a car's headlights shining through a fog so patchy that one moment they're barely visible and the next they're blazing bright again. This dust could come from comets, remnants of a shattered planet, or even colossal collisions in the star's asteroid belt. The irregular dimming might then be the shadows of these swirling debris clouds passing between the star and Earth. Then there's the other camp, the one that sparked headlines worldwide. Could these erratic dips be evidence of something far more extraordinary? In 2015, astronomer Jason Wright floated a provocative idea. What if we're seeing the shadows of a megastructure, an artificial construct built by an advanced civilization to harness the star's energy? The concept isn't entirely science fiction. Physicist Freeman Dyson once theorized that a sufficiently advanced society might build vast solar collectors, Dyson swarms, encircling their star to capture its power. If alien engineers were mid-construction, their partially built array might block starlight in exactly the uneven, unpredictable way Tabby's star does. The debate quickly became a case study in scientific caution versus open-minded speculation. Occam's razor, the principle that the simplest explanation is usually the right one, clearly favors dust. After all, we know dust exists. We've seen it around countless stars. Alien megastructures, on the other hand, remain firmly in the realm of hypothesis. But here's the twist. Follow-up observations complicated the dust theory. When astronomers analyzed the star's light during a dimming event, they found the dips were more pronounced in blue wavelengths than in red, the opposite of what you'd expect if dust were the culprit. Fine dust tends to scatter blue light, making the star appear redder when dimmed, not bluer. This inconsistency sent researchers scrambling for alternative dust models. Maybe the particles are unusually large, or perhaps they're not dust at all but something more exotic, like ionized gas. Others proposed that the star itself might be volatile, prone to massive eruptions that throw uneven clouds of plasma into space. The truth is, Tabby's star is so unusual that even the natural explanations require stretching our understanding of stellar behavior. Meanwhile, the megastructure hypothesis, while tantalizing, has its own hurdles. If aliens were building something massive enough to block 20% of a star's light, whereas the infrared signature, all that absorbed energy would have to be radiated as heat, but searches for excess infrared radiation have come up empty. Plus, the dips don't show the strict geometric patterns you'd expect from artificial structures. They're messy, asymmetric, and unpredictable. What makes Tabby's star so captivating isn't just the mystery, it's the way it forces us to confront the limits of our knowledge. Whether the answer turns out to be cosmic dust, an astrophysical phenomenon we've never seen before, or something even more extraordinary, this star reminds us that the universe still holds surprises we can't yet explain. Every new observation peels back another layer of the puzzle, keeping astronomers and the rest of us on the edge of our seats. Until we crack it, Tabby's star remains a cosmic Rorschach test, revealing as much about our curiosity as it does about the distant heavens. Picture a cat sealed in a box with a radioactive atom, a device designed to release poison if the atom decays. According to quantum mechanics, until someone opens the box, the atom exists in a blur of possibilities. both decayed and not decayed, leaving the cat simultaneously alive and dead. This is Schrödinger's famous thought experiment, highlighting quantum superposition, the bizarre idea that particles can exist in multiple states at once, collapsing into a single reality only when observed. But here's where it gets cosmic. What counts as an observer? And if quantum rules govern the entire universe, why don't we see galaxies or black holes in superpositions? The measurement problem lies at the heart of this paradox. At the quantum level, particles behave like waves of potential until measured, then suddenly, they choose a definitive state. But who or what gets to make that choice? Some interpretations suggest consciousness itself plays a role, as if reality crystallizes only when a mind perceives it. This radical idea, championed by figures like physicist John von Neumann, implies something staggering. The universe might exist in a hazy, undefined state until conscious observers, like us, force it to decide. It's as if the cosmos is a grand stage where the lights turn on only when there's an audience. Others find this explanation too anthropocentric, favoring the many worlds interpretation instead. Here, every quantum decision spawns a new universe. The cat isn't alive or dead, both outcomes happen, but in parallel realities branching away like forks in an endless road. In this view, there's no collapse, just an ever-expanding multiverse where every possibility plays out. The catch: we only experience one thread of this infinite tapestry, never witnessing the cosmic splitting firsthand. Then there's the cosmological angle. If quantum rules apply universally, why don't entire stars or galaxies exist in superposition? Some theorists argue they do, but at macroscopic scales, these states decohere, meaning environmental interactions lock in one reality almost instantly. Imagine tossing a pebble into a still pond. The ripples spread and interfere until the water's surface becomes too chaotic to trace any single wave. Similarly, a star's photons colliding with dust or gas could force it into a classical state before we ever observe it. The implications ripple outward. If consciousness somehow shapes reality, does that mean the universe needed observers to exist at all? Or is the multiverse a cosmic safety net, ensuring every quantum roll of the dice lands somewhere? Perhaps the answer lies in between, a yet undiscovered physics that bridges the quantum and cosmic scales. Until then, the measurement problem remains a haunting reminder that the universe's deepest truths might not just be stranger than we imagine, but stranger than we can imagine. One thing's certain: this isn't just philosophy. Experiments with ever larger quantum systems, molecules, then viruses, perhaps one day even tiny organisms, push the boundaries of where superposition ends and classical reality begins. Each breakthrough chips away at the mystery, inching us closer to understanding whether the cosmos is a singular stage or an infinite ensemble of parallel worlds. Either way, the act of observation, once a passive detail, now stands as one of the most profound forces in existence, a silent architect shaping the universe one measurement at a time. Back in 1930, physicist Richard Tolman devised what seemed like a simple way to test the expanding universe. His idea hinged on surface brightness, the amount of light an object emits per unit area. Think of it like a street light. As you walk farther away, it appears dimmer overall, but its surface brightness, the intensity of light coming from its actual surface, should stay constant. Tolman reasoned that in an expanding universe, galaxies should behave the same way. Their apparent size would shrink with distance, but their surface brightness ought to remain steady. Except when astronomers actually ran the numbers, they found something deeply unsettling. The light from distant galaxies is fainter than Tolman's test predicts. Not just by a little, but by a factor that aligns with cosmic expansion over billions of years. This mismatch isn't just a minor discrepancy. It cuts to the heart of how we understand light, distance, and the very fabric of space-time. If the universe weren't expanding, light from distant objects would simply spread out as it traveled, dimming predictably. but in an expanding cosmos, light also gets stretched red-shifted, losing energy as space itself grows between us and the source. The Tolman test expects this, yet the observed dimming exceeds even those adjustments, as if the light is somehow tired from its journey. That's where the tired light hypothesis comes in. Proposed as an alternative to cosmic expansion, it suggests photons lose energy over vast distances due to interactions with interstellar particles or some unknown quantum effect. No expansion needed, just light gradually wearing out like a marathon runner. But there's a catch. If light were truly losing energy this way, distant cosmic events like supernova wouldn't appear stretched in time as they do in our expanding universe. Yet they do. Plus, the cosmic microwave background's near-perfect blackbody spectrum contradicts tired light's predictions. The hypothesis is elegant, but the evidence has largely sidelined it. So if tired light can't explain the Tolman test's failure, what's left? Modern cosmology points to metric expansion, the idea that space itself stretches, redshifting light while also diluting the number of photons reaching us. But even this doesn't fully account for the observed dimming. Some theorists argue we might be missing a piece of the puzzle, like an unknown interaction between light and dark matter. Others speculate about evolving physical constants. What if the speed of light or Planck's constant weren't fixed over cosmic time? These ideas tread dangerously close to fringe physics, but the Tolman anomaly forces us to consider them. The most tantalizing clue lies in galaxy evolution. Distant galaxies are younger, and if their stars were intrinsically brighter in the past, perhaps due to lower metal content or hotter stellar populations, that could explain part of the dimming we see today. But models struggle to make this fit without breaking other observations. It's like trying to solve a jigsaw puzzle where half the pieces belong to a different box. What makes the Tolman test so compelling isn't just the conflict it reveals, it's the humility it demands. For nearly a century, this simple thought experiment has haunted astronomers, whispering that our cosmic models might be incomplete. Whether the answer lies in tweaking relativity, rethinking galaxy formation, or uncovering entirely new physics, one thing's clear: the universe's light carries secrets we're still learning to read. And until we crack them, the Tolman test remains a ghost in the data, reminding us that even the oldest questions can still surprise us. The universe will end not with a bang, but with an endless, silent freeze. That's the grim prophecy of heat death, the leading theory for our cosmos' ultimate fate. Picture a time trillions of years from now when every star has burned out, every black hole evaporated, and the universe has expanded so much that even particles are too far apart to interact. No more light, no more heat, just an eternal, uniform darkness where not even time has meaning. It's the ultimate equilibrium where entropy, the universe's slow slide into disorder, finally hits its peak and nothing can ever happen again. But heat death isn't the only possibility. Rewind to the early 20th century, and cosmologists imagined a very different finale, the Big Crunch. In this scenario, the universe's expansion eventually slows, halts, and reverses, collapsing back into a singularity, a mirror image of the Big Bang. Gravity, the great unifier, would pull everything together in a cosmic demolition derby, galaxies smashing into one another as temperatures skyrocket. Space itself would crumple like paper tossed into a fire, ending in a singularity so dense and hot that the laws of physics break down. For a while, this idea held sway until the discovery of dark energy, the mysterious force accelerating the universe's expansion. Unless dark energy weakens or reverses, the Big Crunch seems unlikely. Then there's the cyclical universe model, a cosmic phoenix rising from its own ashes. Here, each Big Crunch births a new Big Bang, creating an endless loop of universes, each with slightly different physics. Some versions of this theory suggest collisions between higher dimensional branes in string theory could trigger these rebirths. Others propose that the singularity at the end of a crunch, bounces rather than collapses like a rubber band snapping back. The appeal is obvious, a universe without true death where existence resets itself eternally. But like the Big Crunch, cyclical models struggle with dark energy's relentless push. Enter the wild card, vacuum decay. Deep within quantum fields lies a terrifying possibility that our universe isn't in the lowest energy state but a false vacuum. Think of it like a ball resting on a hill instead of in a valley, stable for now, but one nudge could send it tumbling. If this false vacuum destabilizes, perhaps from a random quantum fluctuation, it could spawn a bubble of true vacuum that expands at light speed, rewriting the laws of physics as it goes. Inside this bubble, atoms might not hold together, forces could cease to function, and reality itself would unravel. The worst part, we'd never see it coming. One moment, everything's normal, the next, an invisible wall of annihilation sweeps through the cosmos, erasing everything in an instant. So which fate awaits us? Right now, the scales tip toward heat death. Dark energy shows no sign of weakening, and the universe's expansion only accelerates, but physics is never that simple. Some theories suggest dark energy could decay, shifting the balance. Others argue that quantum gravity effects near a singularity might prevent true vacuum decay or enable cyclical rebirth. The only certainty is this: the universe's end depends on forces we barely understand, and every new discovery, from the nature of dark energy to the stability of the Higgs field, could tilt the scales toward a different destiny. Perhaps the most humbling thought isn't how the universe ends, but how little it matters to us. These scenarios unfold over timescales so vast they dwarf human history. Stars will still shine for billions of years, galaxies will dance their slow spirals, and life, if it survives, will face challenges far more immediate than cosmic doom. But the question lingers, not just as scientific curiosity, but as a mirror to our place in the cosmos. Are we doomed to fade into silence, or is the universe playing a longer game we've yet to comprehend? The answer, like the future itself, remains written in the dark. Let's talk about a thought experiment so unsettling it makes the Matrix look tame. Picture a single, disembodied brain complete with fake memories, fabricated senses, and a wholly imaginary past floating alone in the infinite void. No body, no world, no universe, just a self-aware flicker of consciousness hallucinating everything you think you know. This is the Boltzmann brain paradox, and it's not science fiction. It's a statistical nightmare lurking at the crossroads of physics and philosophy. The idea stems from thermodynamics, specifically Ludwig Boltzmann's work on entropy. In an infinite universe where particles randomly rearrange themselves over unfathomable timescales, even the most improbable events become inevitable. Given enough time, chaos alone could assemble a fully formed brain or an entire universe by pure chance. The kicker: a single, momentary brain floating in the void is statistically more likely to arise spontaneously than the staggeringly complex, ordered cosmos we perceive. Think of it like shaking a box of alphabet soup for trillions of years. Eventually, the letters will spell out war and peace, but they're far more likely to briefly form the word cat first. This leads to a chilling conclusion. If randomness can conjure conscious observers, how do we know we're not the statistical flukes? Our elaborate universe, with its billions of galaxies and finely tuned laws, might just be an illusion cooked up by a lone brain's desperate attempt to make sense of nothingness. The memories of your childhood, the feeling of sunlight on your skin, even the screen you're staring at right now, all just phantom sensations woven by chance. Of course, physicists recoil from this idea, and not just because it's existentially horrifying. For one thing, Boltzmann brains violate causality. A real brain needs a history, evolution, a body to sustain it, an environment to shape its thoughts. A randomly assembled one would be like a computer booting up with no hardware, running on luck alone. Even stranger, these brains would outnumber real observers infinitely, meaning the odds of you being a Boltzmann brain approach 100%. The universe should be drowning in them, yet we see no evidence of phantom mines popping in and out of existence. So why doesn't this paradox collapse cosmology? One escape route invokes inflation theory. If the early universe expanded exponentially fast, it could have created such vast order that Boltzmann brains become vanishingly rare compared to real observers like us. Others argue that consciousness might require more than just random neuron-like arrangements, perhaps quantum processes or embeddedness in a physical world. Then there's the philosophical nuclear option, skepticism itself. If we can't trust our senses to confirm reality, science has no foundation at all. The Boltzmann brain isn't just a brain teaser, it's a stress test for our models of reality. It forces us to ask what makes an observer real. How much can we trust probability when dealing with infinity? And if the universe is just a fleeting glitch in the void, does that make it any less meaningful? The answer, for now, is written in the cosmic static, a whisper of doubt that keeps physicists awake at night, wondering if the stars they study are just figments of a lonely mind's desperate dream. What if everything, every star, every atom, every fleeting thought, is just lines of code running on some unfathomably advanced computer? This isn't the plot of a sci-fi movie. It's the simulation hypothesis, a serious argument that our reality might be an artificial construct, crafted by entities whose technology makes our own look like stone tools. The idea gained traction when philosopher Nick Bostrom laid out a trilemma. Either civilizations never reach post-human stages capable of running ancestor simulations, they choose not to run them, or we're almost certainly living in one right now. The logic is jarringly simple. If future civilizations could simulate conscious minds, they'd likely create countless iterations, billions of simulated universes for every base reality. Statistically, the odds tilt hard toward us being in the simulation, but how would we even know? Some theorists point to cosmic glitches, tiny imperfections in the fabric of reality that resemble computational shortcuts. Take the speed of light. It's not just a limit, it's a fixed processing speed, like a universe-scale frame rate preventing the system from overloading. Then there's quantum mechanics, where particles exist in probabilistic states until observed, almost like a program rendering details only when needed to save resources. Even Planck length, the smallest possible unit of space, hints at a pixelated universe, a grid too fine for us to perceive as anything but smooth. Not everyone's convinced. Physicist Sabine Hossenfelder argues that simulating every particle in a universe would require more energy than the universe itself contains. But proponents counter with optimizations. Maybe only conscious observers are fully rendered, like a video game loading detailed textures only where players are looking. Others suggest we might be uploaded minds in a historical simulation, reliving some filtered version of the past. It's a cosmic twist on the Matrix minus the rebellion. The philosophical stakes are dizzying. If we're simulations, do our choices matter? Is free will just an illusion coded into the program? Some theologians even draw parallels to creation myths, a higher intelligence crafting reality, not from dust but from data. Elon Musk famously quipped the odds we're not in a simulation are 1 in billions. Yet critics fire back. If simulations can simulate simulations, the chain regresses infinitely, making the whole premise untestable. Here's where science pushes back. Researchers have proposed real experiments like hunting for rounding errors in high-energy particle collisions or anomalies in cosmic ray distributions that might betray underlying code. Others suggest that if space-time is discrete, not continuous, its pixelation should leave imprints on light from distant quasars. So far, no smoking gun. But the search itself reveals something profound. Whether we're code or carbon, the hunger to understand reality is undeniably, achingly real. Perhaps the most unsettling question isn't whether we're in a simulation, but what it means if we are. Does it diminish our lives or make them more extraordinary? After all, even if every star is a rendered illusion, the wonder they inspire isn't. The simulation hypothesis forces us to confront not just the nature of reality, but the value of existence itself, whether it's written in atoms or algorithms. Until we find proof, the universe remains the ultimate open-world game, and we're all players guessing at the rules. From the ghostly tug of dark matter to the cosmic speed mismatch of the Hubble tension, every mystery we've explored isn't just a gap in our knowledge, it's a doorway to something deeper. These puzzles stretch the boundaries of physics, forcing us to question what we think we know and rewrite the rules of reality itself. The Great Attractor's silent pull, the eerie cold spot in the cosmic microwave background, even the fleeting whisper of the wow signal, each one challenges us to look beyond the obvious and consider possibilities that once seemed like science fiction. And let's not forget the smaller enigmas, like the moon's long-lost magnetic field or the bizarre dimming of Tabby's star. These might not grab headlines like black holes or alien megastructures, but they're just as vital. They remind us that the universe hides its secrets in plain sight, daring us to dig deeper, think bigger, and stay humble in the face of the unknown. Then there are the existential riddles Boltzmann brains, the simulation hypothesis, the haunting question of how it all ends. These aren't just thought experiments, they're stress tests for our understanding of consciousness, reality, and our place in the cosmos. They force us to confront the uncomfortable truth that some answers might always lie just beyond our grasp. But here's the beautiful part: every mystery solved unveils two more waiting to be uncovered. The universe isn't just a puzzle box, it's a living, evolving conversation, one we're all invited to join. So whether you're captivated by the hunt for Planet 9, obsessed with the Fermi paradox, or still reeling from the implications of quantum foam, remember this: curiosity is the compass that points us forward. The universe loves a good secret, but it rewards those brave enough to search for the answers. Which of these cosmic enigmas keeps you up at night? Drop your favorite in the comments, because the next great discovery might start with a single question, and yours could be the one that changes everything.